Well, hello, and we're back to our series of videos about how we make a very small JavaScript like language. Actually, trying to do JavaScript but from scratch, and just a very tiny pillar of technologies, like a stack of technologies. We do as a quick recap, from Lexer to type checker and to probably some WASM output later. So now primitive type checking. I was saying about types and type checking, TypeScript and stuff for the last year. So maybe this is time to do primitive type checking. Why primitive is because instead of really doing Hindley-Milner, the most popular and the most flexible type inference technique, we will just do spectacular evaluation, and instead of working with values, we will just work with types. Yeah, so as I expected last time that implementing AST evaluator will take 30 minutes to accomplish something, but it took just 3. I guess that with type checking, especially given that we already know how to go through the nodes, it will take even less, but still it's nice to do. And I guess for the stream 7 that would be our plan. Stream 7, type checking, and maybe we will touch a little bit of syntax highlighting, which is way more complex for our tiny language because we would need to implement so much. Anyway, let's do type checking. And how can we do type checking if everything is in our language currently is sound? So we have only numbers and operations on numbers, and we don't care about division by 0. As we've seen last time, it just gives us infinity. But we already have, luckily, we already have another type in our language. It's regular expression, and we'll see how we can do some type checking using that. So let's go and do exactly the same as the last time. We just need to edit this JS file by replacing evaluation. We don't really need evaluation for now, but it's still nice to keep it here. It's like integration test here, so we don't break at least the basics. So what we can do, we can clone. So type check and have here like type check, exactly the same thing. And we do go to evaluate, and we do some very nice copy pasting. Type check JS, and it goes there. This we don't need, and it will be type check. And here we should probably do, I like it from the Rust course, we do unimplemented function, unimplemented, and there we just throw new error, not implemented, or something like that. Message, yeah. And then when we want to have something implemented later, we just say that we don't really implement it yet, so we don't have the back traces here, we just don't need them. And here everywhere we just say unimplemented, and it should just work maybe like this. It throws, so yeah, all good. Don't need this. I just clean up everything to start fresh and new, and then yeah, so actually almost everything stays. We have a function, we have a visitor which knows about numeric literal, binary expression, but it doesn't do anything but visit. So in the end we can just return, we will not return anything. We need to follow the unimplemented things. And then I just do type check. How do we do type check? We just, I guess, do type check on AST for now, and if anything goes wrong, we just need to return, I don't know, true, false type checks. Let's see. We just return true all the time. Not implemented, that's great. Noise. So let's go to the type check, evaluate we don't need. And maybe we want greedy star, we don't need it anymore. Yeah, let's do type check for just one thing. Yeah, we need a tree. Anyway, nice. So we counter type check and we do root to see what it is actually about. So as with evaluator, we just want to go step by step, node by node, iterate over the tree which we have and fold it. So we find the leaf. It's a node, like some kind of numeric literal, doesn't have nested nodes. We then do something with it. Last time in the evaluator we just took the value and returned it as just value, so we folded it, then we which was a primitive map actually, and then we find something which has child nodes like binary expression, then we fold the children first, and then we fold the binary expression to something what it gives us, and it will be just single value. So it actually does reduce this, does fold the tree. So this is, I'm pronouncing it explicitly because I didn't do it in the last stream, because it's like folding and folding. It's very much obvious, and I think in the first streams I was pronouncing, saying that folding, fold, folds, folding, reducing, map reducing all the time. So it's still nice to recall it, but that's not that necessary. I guess this is why I didn't say that last time, but here we definitely do the same, but just on the type level. So enough talking again. We have our own, we will have our own first unimplemented, and it will be where? It will be, yeah, sure. This one, numeric literal, sure. So it goes deep, and the first time we really need to make a decision is when we have a leaf node. That's, by the way, quite interesting because we do visit binary expression, but we immediately recurse into visiting its left branch, and we don't even come to these unimplemented branches. We just explode on the first numeric literal. So anyway, numeric literal is numeric, right? It is always a number, by the way. Let's check. Do we have numeric literal which is not a number? Value, okay, it will be regexp, token, and numeric literal. Nice. So that we know that it is always number. And what we do, we return, for now, just number. Quite simple. Yeah, so it's just number. We don't care what the value is. We actually don't care at all. We might want to have maybe later an added semantics to that, not semantics, added detail to that, where the type is coming from, and we need to have a lock somehow, and then it won't be just a string, it would be a class, as object of some class which knows where it originates from. But currently we don't need to, and we erase this information because I guess we would not really look into the type checking that much because it's a super deep topic. Anyway, still nice. We return just number because numeric literal is always a number, nothing else. Then what we can do, we go to the binary expression. No, we just run and go to another unimplemented. So it was a div token. Source. I need source. So we went first to here, then to the right branch of plus. There we went to one numeric token, it was fine, another it was fine because they're all now implemented, and then we wanted to fold the first division token, and here we are. So div token, what can we do here? And we have a left type actually in this case, and a right type. We can just say return left type, and go away with that. But actually what we want to check, because we're doing type check, is that both arguments are numbers. This is really what we want. And then we do if left type is not actually a number, then we do some for now unimplemented. Let's follow the logic. And if right type is not a number, we'll also panic. And if everything is fine, both of them are numbers, we return number, and everything should just work. In our case, great. And then we have a different unimplemented for plus token. And I guess we just copy paste it. Yeah, or we just do the old school C style fall through. Yeah, and we get it implemented then. And then, yeah, it just says that the whole expression folds to number. Wow, we did our first kind of type inference, and it just works. Oh yeah, now I remember where the hard part was coming from. So yeah, for this little tiny language where we don't have variables and we don't have branches, it is quite simple. But there, when I was getting prepared to this series of videos, I did a little bit more advanced type checking, and it had functions, so it was really way more complex to even have a first result. And I guess we will have another video when we finally extend the language, and after that video we can think of doing some more fancy stuff. But let's see. I think some generalization over strings we can do even here. So what's there? Source. Let's have then our first mul token. It's the same then. All of them require as to have numbers on both sides. That's great. That's great. And then, and then let's try to have a simple one and add a regular expression. I think we can only parse foos now. Unknown node, regular x token. Nice. Where? Tell me where. Here, sure, because we don't even know how to do regular expression. Very good. Very good. So we made our own life easier a little bit, having this default case. Instead of having some JavaScript runtime error, we have our own internal engine runtime error, but still a runtime error. Yeah. Okay, so numerically true, then we have regexp token, and it would be just regexp. Yeah, and we don't care about the value now. And here the same. So let's not destruct. Should be fine, not implemented. That's great. Where? Not here. This one. Really? Can I just jump? Nope. Yeah, nice. So the right tab is not numbered. Good. So now we need to come up with some error message, and I think we should, for now, we should just throw new error saying that the right hand side value, right hand side, really there is, yeah, wonderful word, and right hand side argument to, in our case, let it be just binary operator, and we say which operator must be of type, must be of type number. Great operator. Then here comes op type. Must be of type number. Let's see. Is it better? Yeah, right hand side argument to binary operator plus token. Okay, I like it, but maybe we can do it more user friendly. Can we? Type plus token. No, it doesn't really save how it was written, but anyway, nice. So good. It throws, which is okay for now. Right hand side argument to the binary. Yep, it does type check. So now when we have a unsound from our perspective, not from JavaScript perspective, application of plus operated to a regular expression, it explodes. Let's now check if we go the opposite. New syntax error, expected token type, and oh, we didn't implement that. That's uncool. We should. Okay. Then maybe we do it like this, or do it like this. Will it work? Yeah, it will work, I guess. Not implemented. That's good. Let's jump into there. No, okay. And that is just for left. Okay, great. Then left hand side. Left hand side argument. Wow. Yeah, it does type check it and throws. And okay, now let's think how we make it look better than just throwing. I guess we should give it the location of where it is coming from, but here, okay, so yeah, we need to extend the logic already, but it's a good moment to add some things to add. Okay, so we do what? Add some very basic type checking. Very basic. Yes, true. Very basic. Good. Now, I'd like to tell the user where the type is coming from, or at least what is causing the problem. And now we have an issue, not here immediately, but we can have it, because if we infer that the expression to the right produces regular expression, for example, type after some application of a function, we don't really want to point the user in a very distant regular expression which made the whole thing fold into the regular expression type, or number type in this case, if we do this as a number, make it as a number. And we cannot model it, unfortunately, because our language is too primitive. But we still should do begin and ends again here. So this should, and this we didn't do in the evaluator because we didn't really care where it comes from. Errors were very much specific to where we execute them, but here types are more like distant, acting on a distance. So anyway, let's I don't know, how can we really make it more explicit? Yeah, I guess not yet, but okay, let's start extending our type checker. Yeah, that's the sweet part, actually. So we should probably have type number, I guess, like this, or yeah, for now. And there, yeah, but this is the same time. That's interesting. I don't really remember how I did it last time, and it was quite smooth. Anyway, let's just start doing this as simple as possible. So we have a type number, and then we will have instances of this type. Probably should work, and then we do instance of all the time, or something like that. Then we have this location equals log. That should kind of work. And then here we just return new type number, and here we really want to have log, and we give it log. Good. Same we should probably do with type regexp. Yeah. And bam, instead of numbers, instead of strings, we now have objects. That's amazing. Yeah, and then we can use some object-oriented programming to decide for us if something is good to have a binary operator defined on it or not. Let's see. Anyway, yeah, we need to implement strings then. That would be a very good, yeah, very good. Nice. So if left type instance of is not instance of number type, if not, yeah, there is no negation, then we know that the left type has some information. So of type number, argument, and now we can say this wonderful at and copy paste again. I'm too lazy. Next time. Okay, good. And then the left one. Was it left one? Yeah, should be left one now. Log is not defined. Amazing. Because this log. So good. New type number log. Maybe we just don't have it there. Let's see. Log. It's undefined. No, it's fine. Should work. So left type. Op type, yes. Op type, probably that was the thing. No. Oh, fine. So add. Log is not defined. Good. And it's not defined. Of course. Yeah, I'm bad at copy pasting, as you remember. Number type is not defined. Wonderful. Type number. Yes. Type number. Already way better. At. Can read property file of undefined. Really? Type, please. Probably because it is numbered here. Anyway, let's see. Type cannot read property. It's object. What do I do there? New regex, wonderful. Peter, yeah, that's better. Must be at source, and we have it. Now, great. Very nice. Now it works. Yeah, using TypeScript would be cool, but yeah, it would save some time for debugging these simple errors. Good. Then we do the copy paste again and do it for the right type. Left type, right type. Yeah, it's quite boring. We don't do it for long. Yeah. Now comes the hard part, this one. We need to infer the type, and currently we cannot infer that much. Yeah. Okay, for demonstration purposes, I would make plus work on regular expressions for now. I guess that should do the trick. So that we have 1 plus 2 multiplied 3, that would be even better. So enough of regular expressions. Yeah, better we say that plus works only on strings for now, and we don't have strings, and we will just complain that the right-hand side expression produces number as a type. So yeah, that means when we have so plus token, it's here, and it doesn't work on type number. It works on type number. I don't want to ruin all of this. How to do it? Okay, all good. So if it is a number, then must not be of type number. That also works. And it will just say must not be type number. That's good. Now the plus token doesn't work, and the mul token will work. Yeah, and we still need yeah. So just for demonstration purposes, mul and div will work on number. And what I want to actually demonstrate, I want us to know that the right-hand side of the plus operator is not just one single token. It is a span. It's a branch, and it's spanned from the beginning of 2 to the end of 3. So we can say later, when we have some beautiful error output, that here the right hand side of plus must be, in our case here, must not be a number, something like this. And we want to say that the right hand side is not just 2 or is not just 3, it's the whole thing again. So let's try implementing this quickly. So div and mul, they just produce a number. How do they do this? They have left type and right type, and they create another type number. Not checking anything, we just want to skip it for now. New type number with location being definitely file is coming from left file or right file. They will okay, in our case it's just one file. Multiple files for later would be too much. And then we have start as left log start, and then end as right log end. Should kind of work. It's not with type, add source. Okay, and here we have just add, right, which points at the full thing, right? Let's see. Yeah, the left type. Okay, we want actually the right type. The left type should be, we ignore left type, we don't care. So right hand side argument blah 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 should not be of type at undefined. That's good. That's good. That means so left actually log file, and it just goes there, and it just points at the start of 2, which is not enough. What we really want to do is giving a span, and this is what we really are doing. So file there, to yeah, from here till here, right log start end line and end column. Bam. Do you have it? Yeah, good. So we jump there, and we know it goes from the 5th till 10th. So like this. Let's see here, column 7, 8, 9, 10. Yeah, good. Feels amazing. Feels amazing. Yeah, so we inferred not only type, let's say, right? When we folded the multiplication, we inferred the type itself, that it has number on left hand side and right, and number on the right hand side part, and it combines into number, but we also save the context where it is coming from, which is really good. And that should be, I think that should be it, where we decide on the location. So probably we should do const log, something like this, and it will always be like this. And this is where the refactoring starts. Log, good. Then we don't really pervert our logic. It's not, so I'm just returning everything back to normal. Just had a nice demonstration. And currently here we don't really want to print it this way. We just want to print where it starts. So yeah, back to normality. And log what has already been declared. How come? New log. No, is a new log is a span log or something like that. Then when we need it, we just return, yeah, here we return new type number with the span log, and bam, type number starts at line column 1, ends at 110. That's nice. So we know that the whole thing evaluates its infers, gets inferred into type number. Great. Still, yeah, we definitely need to extend our language to have more fun with that. But okay, so we can have a nice commit message saying saving context in the type. Nice. Now let's think about it a little bit. So currently we made binary expression know a little bit too much about the type, so we just hard-code the type of left-hand side operator, and the type doesn't know anything except where it comes from. But we also can make it more polymorphic and teach the type to actually check itself. So we can, instead of writing it right here, say that operators are defined as like methods on values. So in general, we just look at this thing and understand that 2 multiplied 3 might be kind of represented as 2 mul 3. So then instead of having this as a intrinsic of our type checker, which knows exactly how class token, how div token, how mul token work, actually operators work in general, it might say, okay, I know your type, my left hand side, and I give you the operation, the message, the method, the interface, whatever I want to have on you, and I give you the right hand side operator as an argument, and then you check it. And I don't need to know, is it a number, is it a string, or is it anything else? For now, I guess we will not do this immediately because I just struggle to illustrate how this thing works. No, we can. all good. I'm fine because we have regular expressions which are like strings. Yeah. So now, all good, all good. We say right hand side must not. Oops, oopsie. Sorry. Must be of type number. Great. Actually, of type number. Can we do it like this? There is name. Something like this. Number. Yeah, I'm generalizing already. Yeah, of type number. Good. So now we having regular expressions. We can model it. Yeah, good. I think we can do it. All good. So let's try. We know that left type is something smart now, and we can just ask it. Let's do only plus for now. So mul token and div token should or not should probably be gone for now. Yes, like this. And then we have here unimplemented. Good. I think that would simplify everything. We can focus. So now I have my left type, and I know that's plus token, and then I just say, hey, left type plus the right type. Right type. Yes, I think. Yeah, and I just do the check there, and I can just do then the throw in it. So left type plus operator. Oh no. Let's do a little bit C++. Operator plus. Sorry, operator plus, and then I go to the function type, and it becomes a class, and it gets constructor where there is the location, and I save the location, and then I have operator plus, which is a function and gets the right one, and then I just copy this whole thing. Yeah, I think the whole thing. Yeah, do I do it? Yeah, so anyway, let's try. Operator plus. Then my right instance of type number, and then right hand side going to binary operator must be of type number. Good. But this is only happening if we are in number. Good. So for the string type, it will tell us that if you want to sum strings, then on the right hand side it should be also a string. Good. So we don't need to do all crazy switch cases here. But what we don't really do is that we don't check the left hand side. So left hand side must also be one of number or string, but this is probably what a specific type cannot know about, and we need to check it here. Thinking kind of yeah, I guess we must do this. So the plus operator and the minus, plus. So actually the minus doesn't work on strings at all. So if we get into the minus, we just don't have it there, and the left type might be of something. And then doesn't implement. Let's see how TypeScript actually does it. So TypeScript lang, and what kind of message does it produce? I don't actually remember. I haven't seen that for a long time. It's very nice. So let's do 1 plus 3, all good. 1 plus string. Really? Sure. Good. Errors. Operator plus cannot be applied to types number and regexp. Just that? Okay. What about minus string? So what does it say? The right hand side. Okay. Yeah. So sorry. Right hand side. Right hand side often. Okay, I will just copy paste. Must be of type any number begins or an enum type. Wow, that's way more advanced than what we can currently implement, the right hand side of an arithmetic operation. So yeah, here I can see that our approach doesn't really work, because it will say that left hand side of an arithmetic must be of a type. Okay, but this is like, yeah, this means that minus knows its types, and we need to hard code it. So it's number and number, and then what about the plus? If it's plus and then string, this I don't like. And what does it say? Cannot be applied to types number and string. That's better. That's better. Cannot be applied in general to types number and regexp. We can probably do this one. Cannot be applied. And how we do it then, let's just copy that. That would be better. It's simpler, and it might be a very good illustration. So instead of producing the error ourselves in this operator plus, we just say if it fits us, and that's it. And yeah, I guess we can do it like this. Class base, type base, something like, yeah, type base, and we don't have constructor, and we have operator plus, which always says return false. Kind of says, yeah, I don't have operator plus actually. I know about this method, but I don't have operator plus. And what is extends type base? Yeah, and here we just say that right is instance of type number in our case, and that should be fine. Yeah, I like it. Probably this is it. And then the constructor, they all share the same constructor. Can it be like this? I think it should be. Let's see. Then we have class regexp type extends. That's it. Yes, good. So I think we can have a base class for now for our presentational purposes, which just says no to any kind of combination of any arguments to anything we can do on this type. So this type has knows about all the methods, but it just says no to anything. That's fine. And here we simplify this logic to if left type. So actually, we already have it here. If not, left type, right type, we just say throw new error, like this one. Operator plus, good, now we know that it's plus. Cannot be applied to types. Nice, nice, it's quite cool. I like it. And then we have there left type, I don't know, name, something like this. Left type name, and on the right side we also have right type name, and then we just define it like name here, which returns type base. Or we better just throw it here and say it's unimplemented. Oh, how's unreachable? Shouldn't be reachable. Unreachable. And then we throw new error. Unreachable. Yeah, we should never ask name directly from a type base. It's kind of equals 0 in C++, I guess, or must implement something like this. And here we have name, and it will be just number, and there it will be just type regular expression. Self-constructor name pops into my mind. Yeah, we can always refactor this, but now for explicitness we can have it defined in a cool way. So now, yeah, when we get into plus token, we see that we just check if operator plus can be applied on the left one plus the right one, and then we say that it cannot be, and throw and stop type checking, which we should probably not. We just need to come up with a better idea, but now we just stop immediately. And then we return new type number span law. Yeah, kind of looks good. Parade plus cannot be applied to types number and regular expression. So sweet when you check up how it's done properly. Parade plus cannot be applied to type number and number. Damn, why not? Okay, right instance of, because I don't return it. Yeah, I coded a little bit of Rust and get used to this Ruby style returns last expression value. Then it's working. And you can see that we now have a more abstract DSL-like language where we can just define more types. And here we just don't care what type comes in, and of course this thing can be then defined by user of our language using some type definition expressions, right? So we can say that something is defined on a class, and we can infer this from the code and have a, here it's the definition of types static, but we can make them dynamic and extend them on as we go, save where type itself originates from. So when we do the hover, we say, and it's an object of some user's custom type, we just say this is where it is coming from. And here we don't have, we use the lock for actually source of the expression itself, which is probably not exactly the type. So we probably would want to have a double layer thing. It's type as type itself without knowing the location at all. or the original location of the type definition, which is global then for all instances. And then we just have one instance probably which wraps the expression somehow. I don't know. For this we should probably look into how TypeScript does it, so to not re-implement the will that much, because they usually do everything correctly and nicely, and we've learned already that this is one of the best ways to apply. So actually what I can infer from this inference is that the plus was applied on maybe type number, and then it got the regexp as argument, and then it just says nope, it doesn't work for me. That's it. Just relax and let x equals, and then it will be any, right? Yep, it is any. If it's 1 plus 1, it just returns type. Yeah, great. So now coming to any's. Left type operator plus, that's great. It works. We should probably also not stop our type checking on the first error, and it is quite easy to do, I guess. But we have still unimplemented. Anyway, yeah, let's do it. Let's do copy pasting. Mul token and div token. That's great. No. One last thing. So we applied plus token, but we didn't. We checked if everything is fine, but we did not really allow the operator plus to infer the type. So it's polymorphic on the check, but it is not polymorphic on the return type. So we always have the type number here in the op. So I guess what we can do is that we don't return just the bool. We return a type here which gets inferred then. So if right is instance of number and we are the instance of number, then we just return type number. Otherwise we return, for now we return null, something like this. So I guess we should get something like this, const new type equals this. If no new type, something like that, we just scream. We just scream. Cannot be applied, all good. And if we don't scream, we should return this new type, new type, and we gave it span lock, and it's type number in our case. That's great. Then for demonstration purposes, again, so first let's commit. Let's commit. So you can say, okay, add some polymorphism to types. Great, that's nice. That describes it. So I think what we should try to do is we can, for example, allow regular expressions to be combined. Prelude cannot be applied to type number and regular expression. Why? Because it's a plus. Yeah, then we probably need to do multiplication not implemented. Great. Good. For mul token, it will be exactly then the same. And for div token, it's exactly the same. So let's do then this plus token, mul token, div token, we just need to call different different method and put here a different copy pasting again. Yeah, sorry, I'll cover mul token here. So div token later, then operator mul, and then operator mul here. That's good. Saving and undefined new type. New type. Okay, did I not? Yeah, I'm very bad at copy pasting. Undefined new type has already been declared because const. Really? Yeah, sure. Yeah, okay. Yeah, good to be home. Operator mul is not a function. Great. And then we have yeah, here we should do null, operator plus, and operator mul. So all of them just don't work. We've created new operator multiplication, cannot be applied to types regexp and regexp. But now we will actually implement multiplication for regular expressions, and we don't need to touch. Now it's completely polymorphic. We've done this once, and we forget about it. We just go to our type, and we extend it, saying it's operator mul. What it does, it checks if the right-hand side is also of the compatible type. In our case, it's also regular expression, and then we return ourselves, and it just works. Can it be applied to number and regular expression? Good. So now multiplication works on regular expression. Somehow it produces regular expression. Fine. We can actually teach it to produce something else if we already know about type number and regular expressions built on top of it. We can say, and then it will just unknown node type regular expression token. Should have worked. Okay, I will not do crazy things. It's already too complicated. Operator plus cannot be applied to number and regular expression. Good. And that's actually it. And if I add 0 here, can be applied to regexp number, multiply. So it just works. Yeah, and it wraps and returns regular expression on the right-hand side, and then we can actually support the selection. Yeah, nice. And then div token does the same. All good. All good. All good. I think that's very nice. Operator mul. Actually, we don't do this. Good. So yeah, there we should probably have method calls and lookup and let's see, and then everything like this. So can it be applied to types regexp and regexp? Very clear. Thank you. 1, 2 multiplied by 3 should work. It can be the number. Nice. Okay. Operator type regexp and then read number. Just go and say that. Right. Can we make it more robust? Is it something type of this constructor? Then number. Good. So it checks as number, turns null if it's not. Good. And then it's type number and location. Span goes, actually it's not location. From left to right. Good. And evaluates to 7. Yeah. I don't know about you, but is there any more unreachable or sorry, unimplemented? Yes, there is one. For div token, yeah, let's do simple copy pasting. So if we come back to this code in like 6 months, again, I don't really want to debug it. Operator div, and operator, how's it? Div, right? Yeah, div cannot be applied, so first we just do it like this. And not implemented, yes, good. And then I didn't save, so should be good. New type, spend log. Okay, nice, div token. Then we just have operator div. Okay, good. And number, that's the div. Yes, good. Just works. Yeah. Oh, good. Fine. Kinda implement div and all good. So now comes the question, if we have more than one error here, and how do we deal with this? So it's like 1 multiplied by foo and 2 multiplied by foo. By the way, why do I use foo all the time? Because I guess we had a very primitive parser for the regular expression. Yeah. So I must fix it. Bar, if it's the same length it works, but with one's expected token, yes. Okay, next time. Foo bar, they work, they just ignore the letters. And we have just one error, and it comes from cannot be applied to types, and we don't say where. We swallow that, that's not good. We should should say that, and how we do it. Location, we use it a lot here, so finally it's time to move it out. Function log to string location, and then we just return it. Okay, log file, log start. Okay, log to start, because it's just one start, and we can replace it everywhere. Add op log, something like this, yes. And it doesn't end because of this. Great. Log, in this case it will be node log, node, and here we will copy paste everything again. Should not be broken. Yes, good. Can be applied, and at, and then we have it's not actually at, but that's interesting. That's interesting. How does TypeScript do it? It's just okay, good. It just selects the whole expression, which is a good way to go. That's enough context. We don't really need to track if it's left or right in this very general sense. So we have the span log already, and we just say add this thing everywhere. Still can be abstracted. We can of course just produce wrapper, we try, then we throw, and then we say which has failed, and yeah, but we do some copy pasting to just avoid too much abstraction so we can finish in time. Cannot be applied to types number and regex add source 1. Yeah, 1 source.js 1. Yeah, good, works. It's 1, yeah, good. And another one will be somewhere else. So I guess now instead of just throwing, we can think of just producing a set of strings. And I think we should use closures for this. So we have const errors, and there we have just number of errors, and that's it. And we continue. Errors push instead of throw. Then we always return some kind of type, and I think that should be that any type. Return new type any. I guess we don't have it, but let's follow the logic. So we can kind of return any, or we can return this, not mixed, this unknown, which is a little bit better. But if we return unknown, and unknown is guaranteed to have no methods implemented on it, and except for any, no one actually wants to play with unknown, we will have a cascade of errors. So it shouldn't be really unknown, because it's more like if you know TypeScript, it's more like user level type, and we should probably have our type kind of error, something like that. So if you need to transform error to a type and it's really required, then it might be decided on spot. So type error, okay, good. Type type check error, something like this, and it is a type, so it has all of these things, and it looks like the base class extends type base, and it will have null, so it's impossible to check it, and it always returns. No, I think it shouldn't be. Oh, let's see. Let's just see it. Type check error cannot be applied. Nice. So we return type check error here. So error push, throw new error push, and here also error push, and then we return new type check error. New type check error, and new type check error. Unreachable, wonderful. It's good because we checked. Yeah, we violated our own contract. So here our own safety net already tells us that we made some mistake. Return error type error, something like this. What will it say? What will it tell us? Unknown node type regular expression token at visit at here evaluate. What? Oh really? Oh. Nice. Good. So plus token. Yeah, we are now in the evaluator. Yeah, let's fix it. So what it should be fast. It's just so I know for now we shouldn't focus on that, but it's nice to just have none, and it's all fine because regular expression, la la la. So if we return 0, it works. Yeah, at least it is the value, and let's see if the value is what we expect, and it is undefined. Oh, really? Then node. What is there in it? Ah, our regular expression token doesn't have anything. Nice. Then for now, we will ignore the value and the node at all, and we will return unimplemented, something like this. It will just still have none because it works, but we have type check error, so it will in our language that won't compile. So it will compile, but it won't. Okay. And we log type check. But actually, what it does, it should do for const error in errors, and then it will just say console log type error. Type error, then error. Yeah, good. Or better if, okay, const type errors. When we have it, and if we have the sum of them, we just print console log type errors, and then we just indent them to in type errors, console, bam, done. None, good. Why? Because our type checker doesn't really return the errors. Now it will, instead of returning the type of everything what we actually don't care, see, we return what will be the type of the whole program. Do we care? Not at all. If no errors have happened, that means the type will be something sound. We just don't care what it is, and we return type errors 0, 1, and 2. Very good. Well, what's wrong? Because I said in. Yeah, sorry. Again, it's something. Okay. Operator cannot be applied to types number and regular expression at there. And then another meaningful one, operator multiply cannot be applied to, we can actually do division here, will also work. Yeah, so one is the multiplication, one is division, and number and regex. So we can even do bar regex and number. Yeah, so regex number, so that we have supported all the combinations. But then this one is not what we want to actually have. We want to stop propagation of the error. This is why in the initial versions of, maybe it still is, I don't really know, in TypeScript, the inferred type of an expression with a type error is an any. So that if you have an error type, that's fine, you will have the error coming from somewhere, but then everything else will be just any, and we don't care. But it is not exactly any, right? It is something different, and it's not unknown, because unknown does exactly what we do now, because we've implemented our type error in a way that it doesn't support anything, so it's kind of like unknown. So this is type based, but it is different in our super minimal type system. The only difference that it doesn't have name, but it's actually, it doesn't implement anything. It doesn't play well with any other type, even with itself. So it is unknown, and this is why everything high in the tree will complain, because come on, it's an error. But what we can do, we can teach our type checker to be actually behaving like any, but with maybe later some exceptions. But then why don't we just, yeah, let's just say it's any. Yeah, so it's any, and then it just works because any should, and we just implement any as everything is fine. It just returns any all the time. So it has plus, it always returns type any. Mul and div, it's always any. We don't have error anymore. Yeah, temptation is so strong. You want to have any as a solution, at least in the beginning. And we definitely are way in the beginning. Bam, we don't have problem anymore. And then what is probably interesting to see here is that the type of the whole thing, of the whole program, will be type any. Yeah, this is expected. And we can somehow then check that this is really true. And if we have type any somehow and we don't have errors, it is still an error, and then we just panic. Come on, something. If we agree that we don't give the user of our language the ability to define any, and it's an illegal thing, then we must check if it's not any. I think that's a good idea, because think of this. Imagine that we decided to make a very sound language, like controlled environment, and we made any as then, and there is no any. You cannot define any. You cannot use any. But it is very easy to create your own type as any, like this. We say that type any is like type of some function foo, right? Then we have function foo, which actually produces a type error. We do 0 defined by a regular expression, and bam, the type any leaked into a user accessible type system. And then you can easily say that let x of any, and then you do some gibberish here, and everything is any, and everyone just does it because it's fun. And then you have two different languages using exactly the same evaluated type checking. One is type safe, one is not. But as we know, if anything is any anywhere in your tree, then everything must be any in the end, and we actually don't check it. Because number will just say that it doesn't like any, but then it will produce any again. So yeah, it is invariant then. Whenever we have any, and any doesn't play well, so it always produces any if it is if it is a decider for the type inference, then it produces any, and everything else, when it checks, then it we don't have any mechanism saying that I'm okay with any on my as my argument to my type, then it always will produce any because we just don't check. Yeah, it should work. Should work. Should work. And yes, somehow until we have unions, because yeah, this is definitely out of scope for today. Yeah, I was able to stop myself from that. That's good. Nice. So what we have? Let's recap. We have type errors, and they have locations. Let's double check. Yes, good. And actually, we don't see this, but they have actually spans. And next time, we will either print it in the console or maybe do something even fancier. Let's see. Probably the console would be a good starting point. And instead of having just this plain white and black messages, we also find a string, the line from the source, and at least do this nice underlining without coloring for now, but probably it will be the coloring, the syntax highlighting there. All good. It works. It's polymorphic. There is some copy pasting here and there, but this is fine. Type system, when we need to touch it, we just go to the type definitions instead of the visitor, which is great. It warns us when we make mistakes by using yeah, so that was theoretizing completely. We just don't want to make a type sound language now. It's fine to just what type errors? Visit you. Okay, definitely visiting is nice to keep. Yeah, then it's nan, not number, and that's completely fine. It works. Yeah, I like it. Parser, now we fixed. Did we fix it? No, we didn't fix it. Alright, so let's commit. What we did, we implemented implement any type any for error propagation. So yeah, any type looks very much similar to what we had as an exception in the evaluator. So if something is going wrong, we have another return type, very special one, which we handle a little bit specially. So I guess how we could guarantee that if something returns any, then nothing else can overwrite it. We can just wrap the visitor and see that here we do the visit. And then when we call the handler, we know that something has returned an any somehow, and we just don't allow it to return anything else. This is what we probably will do if we need to do more advanced exceptions. We just mark the visitor as any all the time, so we cannot then hide the creation of any anyway. So we can have a decorator for each and every call to the binary expressions, and we can then see if within it there was any inferred, then we guarantee. Maybe at the debug mode, because it will be probably some performance penalty added, and then we just check if everything works, then we just remove it, and after some fast testing or something, we see that it is almost always true and define our language as sound. Great. So that's, I think, it for the primitive type checking. Syntax highlighting next time. So for those of you who wanted to see the primitive type checking, that's it. What I will do while I have like 5 minutes, I will finally fix the regexp to look for the following symbol. So we see that this is that might be a regex. We look at the slash, then we eat it. We don't care about it. Now we are on the first. So example, we do parse foo. So char foo is actually slash. It's easy. That's fine. Then we parse f. And we check, those examples, they just don't work. So if it's slash, that's good, we eat it. If the next one is also a slash, then we should eat it too. Read comment. Really? Yeah, we should eat it too, yeah. So, we just swallow it and give the read comment start, and the read comment actually parses everything except for the first leading slashes. Should work. Let's see then what we do. Okay. So it is not slash. That means it's our first letter, and we just need to save it somewhere. That's good. So we have what we have, let value equals empty string. Yeah, I will put each character into the value one by one, creating hundreds of temporary strings. That's not good. We should probably remember the starting point, the end point, then do one substring.